Time we started talking about how to extend these ideas of risk minimization or empirical risk minimization to the classification problem. And the idea is there are a couple of difficulties. One is this loss function in the case of classification. The usual loss function is not smooth like the quadratic loss. And the other problem is that the function that we are looking at is also discrete. So it's so the optimal rule is like that. So this part is pretty simple to work around. So we want to have a parametric model, something like a linear model for classification. And so the idea is that we can model this a dot x. First, we think of it as a linear function, then we'll realize that the linear function is not going to be bounded in to 0, 1. The simple solution is to apply a function that maps R to 0, 1. We start from some linear function of x, and then you apply a map, the sigma, which could be any map that maps 0, like R to 0 to 1, but like a particular choice is this sigmoid function, which is very common. Why it's common? Because it's easy to work with, perhaps. And so if I model the regression function as sigma of theta x, then I'm effectively modeling what I'm saying is probability of y equal 1 given x is equal to x is sigma theta transpose x. So this is a model for the conditional probability of y given x. And this is sort of enough for us to basically connect it back to ERM, as we'll see. So another way of thinking about this is that we are, if you go back to the very beginning, so we have, so another way of thinking about this. So we have xy, which is from an unknown distribution. And we get a training data IID from the same distribution. We want to figure out this unknown distribution, or as we have seen, the conditional distribution of y given x. So this distribution can be described as the marginal of x, and then the conditional distribution of y given x. So if I have, let's say, the marginal distribution of x, and then the conditional distribution of y given x, these two pieces of information characterize P. So in this logistic regression and also in the parametric models that we'll look at, we're going to assume a model for this quantity. You can also assume a model here, and we'll do that when we want to generate the data. But for building the model, writing down the empirical risk minimization problem, you only need to specify that. And in order to specify this joint distribution, in the case of classification, it's enough to just specify the probability of y is equal to 1, given x is equal to x, because a question mark. Why is it enough to just specify that? The claim is that this completely specifies the conditional distribution of y given x. That's two values. So the probability of y equals 0, given x is equal to x is 1 minus this. So I'm effectively specifying the entire joint distribution. If the problem becomes more complicated, let's say if I do multi-class classification, which we'll do next, it's not enough to just specify this. If I have, let's say, 3 classes, I have like at least 2 independent probabilities I have to specify. If I have C classes, I have C minus 1 numbers that I have to specify. The last one is going to add up to, like, together they add up to 1. But in the binary, so for binary classification, binary classification, it's enough. It is enough to model just the P of y equal 1, given x is equal to 1, in order to specify okay, so this is going to be our approach, trying to specify this using parametric family that's simpler than knowing nothing, or like the Lipschitz sort of condition. And in this case, this is equivalent to specifying this or specifying basically the eta. In this case, the regression function. It's enough to specify the regression. So this is specific to the binary classification. All of these things are basically boiled down to specifying this quantity that we have specified. Okay, so I have this. Now, how can I connect it back to the ERM? So now I want to fit this to the training data. Okay. And I want to basically rewrite a version, right? So I want to have some sort of a, so we want to arrive at a form of at an ERM for this model. So I want to have something like 1 over n summation I from 1 to n, some loss of some sort applied to yi and let's say eta theta if you want of xi, and then argument over this theta. So there is a parameter theta that we need this way, and I want to like be able to provide something like that similar to the regression. So you have a loss function, you compare yi to the this is going to be our estimate, or you could have a different thing. So you can have, for example, y hat I, which is let's say 1 if this is bigger than 1/2, and then compare it with y hat I. But we'll see, like these things are sort of, in a sense, equivalent. But I want something like that. The question is, how do I get there? And before getting there, what is a good approach? So suppose I have training data x1, y1, xn, yn. So from this model, so I know, for example, the probability, I'm going to write it like this. So the probability of so let me write it as T of we'll do that later. Okay, so let's do this. So I just know that the probability of yi equal 1 given the small values x1, y1 up to xn. yn. So I know the probability of yi equal 1 given xi is sort of sigma theta transpose xi. So according to my model, these are IID and the use of the distribution that solves. So I know these are IID and this holds. So how can I estimate this parameter theta? So given the ARM, let's say you're a statistician, you're given this parametric model, and you want to estimate theta. What is the general approach that statisticians? Maximum likelihood, yes, okay. So that gives me a very nice recipe for arriving at an ER, like a rigorous minimization for these parametric models. How do I write the maximum likelihood? So a good approach is the MLE. So if you think of the MLE, let me maybe set it up a little bit. So what we really do here is you're specifying these conditional distributions. So in the end, I'm going to have a joint conditional, let's say, probability mass function or distribution. This is probability mass function of yi is given xi up to xn. So everything is going to be conditional on the x, similar to what we have been doing before, because we're not specifying the marginal distribution x, we're just specifying the conditional distribution. So I'm going to have a valid conditional distribution of the vector y given all the x's. Okay, and this is a conditional probability mass function. So what this means is I could put like 0 ones here for each of them. And then this gives me the probability that I observe that particular sequence of 0 ones. Given all these. Because we have a model for this. So what is the model? So graphical model is that x1 sort of gives me y1, x2 gives me y2. So they're independent. So there's no connection, for example, between these two guys. So once I condition on the x's, yi's are still independent. Okay, and they have distribution that we know. So how can I write this? Okay, good. Product of I from 1 to n. I'm going to use the same notation. It's a little bit not too kosher from mathematical perspective, but like this is marginal distribution or marginal Pn from y given xi. So I have these marginal Pnx. I multiply them, I get the joints. Okay. And this factorization is because of this IID. So the distribution factorizes because of the IID or because of the independence assumption. They're actually not IID. So what I see like the x's are not IID. They're not identically distributed, but they're independent. The reason why they're not identically distributed is because these x's are different, and you can see the probability of y I being equal to 1 depends on xi. So the probability changes for different x. They're independent. They're prior sort of conditionally. Sorry, they're the IID, but once I condition on the x's, things are still independent, but not IID. Right. So now how can I write this in closed form? One more step, yeah. So the thing is, this is the probability mass function. So y can take values 0 to 1. There is so another way of stating this. I want to be like a statistician, I would write it as yi given xi is a Bernoulli. Like this. Okay, so it's a Bernoulli distribution, and there is a compact way of representing the problem mass function of a Bernoulli distribution that statisticians like a lot. So anyone? So detour. Imagine that y has distribution Bernoulli P. I'm going to write a PMF of y compactly. Yes, p to the y times 1 minus p to 1 minus y. Okay. Why is this good? Because y takes value 0 to 1, or 0 and 1. If y is 0, This is actually not correct, right? Is this correct? Yes, it's correct. So y is 1. 1 minus y is 0, so this goes to negative. Y is 0, this goes to negative 1 minus. Okay, so compactly already. Okay, how many people have seen this? I've seen, okay, maybe. This is very useful. So given this now, how can I write this? You have a product here. Someone tell me how to write this down. Yeah, maybe someone else. So you already know. How do you write it? Given this compact form.
Do you take the log?
We'll take the log shortly, but at this point, how can I write? Just this quantity. I want to write it compactly like this. So that's what we have there. Right. So this model is saying y given x, y is a Bernoulli with a certain mean. Does someone tell me what this is?
Substitute.
Substitute. So let's substitute. Just walk me through it. So what is it? Okay, what is that? So sigma, right, theta transpose xi to the power yi times 1 minus sigma theta xi to the power 1 minus yi. Okay. So this is just this formula with p being the sigma and then y just yi. Okay. So that's a nice way of writing the likelihood that. So this is the PMF. So what is the likelihood now? Let's see how many statisticians we have. So what would be like the statisticians mean by likelihood? Likelihood is the same thing for you as a function of theta. Okay. So you assume that you observe the sequence. So you want to basically measure how likely it is on your different parameters. So you view this formula as a function of theta. As a function of theta for the fixed sequence of observations that you saw. If your training data is a fixed sequence, so view it as so when viewed as a function of theta for the fixed observation, x1, y1, or xi, yi, I from 1 to n, this is the likelihood. So likelihood is very close to the PMF or the density, but it's not the density. So density is like a fixed theta and viewed as a function of y. So that tells me what the probabilities are. I can have multiple yi's. So y1, y up to yn can take any values, and I can tell you what is the probability of each observations. Likelihood is like a statistician's view, which is like the inverse or the opposite. So I observe this y1 up to yn. Now I want to see which parameter would make this more likely. So I'm going to look at different parameters. You fix y, I1 to yn, and then the x's are fixed, and then I gravitate this. As a function of theta, this one is talked about. There's a subtle distinction, but it's very important to figure out. Okay. So the statistician doesn't see multiple yi's; they just see the observation is one observation. But I have many different models. When I vary theta, each one of the theta, if I change the theta, I get an entirely different probability model. Okay, so the probability model changes. I want to vary theta, and under each one of the thetas, the value the probability of the given sequence. And then I decide which of the thetas for each of these models would give me the highest probability for this observation. So that's the maximum likelihood. Okay.
So this, semantics kind of thing, likelihood would be only when we talk about a single observation and its behavior under different states.
Yes. Yes, so you observe it, like you fix the single observation, so you saw, and then you vary your parameter to see each one of the, what does each one of the models tell you about the parameter? What is the probability? So in short, it's just that viewed as a function of data, that would be the like fixed data viewed as a function of yi, that would be the probability. Yeah. So if you understand what the likelihood is, maximum likelihood is just maximizes the likelihood, which is that function of data. So if you read as a function of data, you maximize the data that will be given. The interpretation is that I'm finding the data, aka the model, under which this probability is maximum. Okay, so you find the model which maximizes the probability. So maximum likelihood. The parameter or estimator. The parameter or model that maximizes the likelihood, which is that function of theta. So I'm just looking at the function of theta, and you can see you get the optimization problem. So that's where the ERM idea comes in. So in general, let me do more generally. So the maximum likelihood idea. So this part is gonna work out for us in general. Let's see what I called this here. I'm gonna call this Ln of theta. So when you view this as a function of theta, it's the likelihood. Okay. And the maximum likelihood is saying minimum or maximize Ln of theta over your parameter, and that would be the MLE. So view it as a function of theta, maximize it, and that would be the MLE, the estimate. Okay, and this is equivalent to arg max. Let's say I can say 1 over n log Ln of theta. So this is the same thing. So if I take the log and divide by 1 over n, why?
Monotone increase.
So log is monotone. So I'm not looking at the maximum value, I'm looking at the argmax. So the value of theta that maximizes. So the value of theta that maximizes doesn't change because this is a monotonic transformation. And this is also equal to argmin. So this is called the log likelihood. Right? So I can maximize the log likelihood instead of the likelihood, which is fine. And I can also minimize the negative 1 over n log Ln theta. Okay, why? Because this just flips the direction. So if this is decreasing, this is going to decrease. So if I try to increase this, it's going to try to decrease this. Right? So if you think about this, that negative sign just splits the max to me. So it's like minimizing that. And if you look at this, you can see this has the interpretation of loss. So trying to minimize. Okay, so this is called the negative log likelihood, and it's a form of a loss, negative log likelihood. And if I plug in that product rule, right, or product form, which is going to be true for many of these parametric models that we have, I get something like this, okay? So just plugging in this product version, and if I have log of product, things will simplify, okay? Log product is sum of the logs. So this is really going to be argmin theta minus 1 over n summation I from 1 to n. I'm gonna put the minus inside. Log p theta yi given xi. Okay, now this very much looks like NER. So if you think of this as, so this is 1 over n, like it's an empirical average of these quantities. So this is really a loss. So it's like yi and I can call it theta or whatever you want. It's a loss between my parameter and it's actually like it's hard to write it, but let me not write it, but it has this interpretation of a loss. You get a training data point, and we'll see. Like when you write down the formula, this exactly gives you a loss, like empirical loss in the dimension. But this is the general formula, and I just want to point out that all these parametric models that we'll see fall within this category. If you look at the negative log likelihood, or try to minimize the negative log likelihood, which is play out the MLE, this gives you like a recipe for risk minimization procedure. So you write down a parametric model, you do the MLE, you get the NER. So, let's see what happens. Any questions? It becomes a little bit clear if I plug in what that is. But, so in classification, for example, in logistic regression, so the one that we're looking at is logistic regression. So maybe I forgot to mention. So this particular form, we assume this is called logistic regression. So in logistic regression, we have sigma, we have p theta of yi given xi is that quantity sigma theta transpose xi to the power yi, and then 1 minus sigma theta transpose xi to the power 1 minus ii. So if I take the log, right, I put a log here and I put a log there. So what would happen here? The log breaks up the products and then the exponents come down outside, right? Maybe someone can tell me what will happen here. Sorry.
Sorry, log sigma theta.
So you get yi log sigma theta transpose xi plus 1 minus yi log 1 minus sigma theta transpose xi. Okay. And then I can collect the terms that contain yi. I would get yi. There's a log of something minus log of something else. So if you look at this term and this term, right? So log of something minus log of something is log of the ratio. So I would get log sigma theta transpose xi divided by 1 minus sigma theta transpose xi plus log 1 minus sigma theta transpose xi. Okay. So at this point, if I plug that in, so there are different versions. So even if I just plug it at this point, so let's say I plug it at this point, before doing that simplification, what I would get is theta hat is argmin theta let me define something here. So I can say I can write it as I from 1 to n. L BCE yi and then g theta of xi. That's one version where LBCE is takes a y and takes a p and just outputs minus y log p plus 1 minus y. Another minus here. Log 1 minus p. So forget about the simplification first. So if I define this as called binary cross entropy, binary cross entropy. If I define a loss like this, which takes a y and a p, and outputs this quantity, which is, you can see the negative log likelihood of Bernoulli, then I can just write, because I get negative of this when I plug it in here. So I get 1 over n summation I from 1 to n. Something like that where g theta is xi is just sigma theta transpose xi. We could have called this eta theta if you want. So we should call it eta theta. A little bit better. Right, so we have managed to write that in a form of an ARM, so you get the y. And this is evaluate, this is like your regression function. This is very similar to what we did in regression, where we had so you'd have like yi minus eta theta of xi squared, or f theta of xi squared. Okay. If you go back to the regression, so regression, like linear regression, it was theta hat arg mean, summation I from 1 to n. And it was like yi minus eta theta of xi squared, where eta theta was theta transpose x. We call this f theta. So that was linear regression to quadratic loss. This is logistic regression with the loss that comes out of the end of it. Okay. So they look very similar. And we managed to figure out this particular quantity. So this takes an interesting view. It's just that you're doing the same sort of procedure, but you're changing the loss, right? And this part we are also changing the word. Okay, the interesting thing is that I can absorb this sigma into this and I get a different loss, and it will be very similar to this. So this is like I should perhaps maybe call this let's call this f theta. I just want to make sure this might be better. So this is f theta is the regression function. Here we're going to call this g theta because it's not exactly like f theta, but we call this g theta for simplicity. Okay. So these two. Okay, questions? Back to the simplification. Is this so far clear? So I wrote this as basically negative LBCE of yi and sigma transpose, sigma of theta transpose xi. Then I can simplify my life a little bit. So, or let's say if I do negative here, let's do negative. Negative would be negative here, and then negative here. This would be equal to. Okay, this is very useful, and you'll see like if you do PyTorch, this loss is defined, and you can just use it. And so it's a loss between y, which is binary, and p, which is in 0, 1. So it measures. It's not a loss between the binary and binary, right? It's binary, and it's probably. I guess you can have these kind of losses. It doesn't have to be, the loss doesn't have to take the values that don't have to be in the same space. So this is the decision, this is the probability of this. Into this compound actually. Question. So everyone happy? How do we get there? So start from the MLE, it gives you a blueprint. You have a parametric model, write down the MLE, and oftentimes it leads to an optimization problem, which is in the form of an ARM. If you have this independent sum, then we get the log of the product, which gives you the sum. And effectively, it's just average. This is like computing an average over. So this is going to converge to the expectation by the law of large number and logs. Okay. And you can see that if you take the and go to infinity, converges to the expectation, you're not solving the original 0, 1 loss problem, but you're solving a new problem. So the original problem, you replace the loss with something else, which is smooth. And so it's like story gets lost in classification. What else can I do? So I'm not gonna simplify this, and instead of doing that at this level, it's easier to just work with this. So simplification, let's clear this. So instead of working with, so I don't have to worry, I'm just gonna look at L, B, C, E of Y, and then sigma of some, let's call this Z, I believe. Yeah. So these terms, you can see it's of this form where Z, like replace Y with YI and Z with G theta. So let's see if this simplifies. So if you have this, then this is negative Y log sigma Z plus 1 minus Y log 1 minus sigma Z. And so it would be equal to negative Y log, I'm going to collect the Y terms. 1 minus sigma Z plus log 1 minus sigma Z. And you can see now why this form is useful. So sigma Z is 1 plus e to the negative t, or z, sorry, which is also equal to ez divided by 1 plus ez, right? In particular, 1 minus sigma z from the second expression is 1 plus ez, right? So then log 1 minus sigma z is just what? Minus log 1 plus ez. And then sigma z divided by this quantity. What is this? 1 minus sigma z. E to the power z, yes. So just consider these two expressions to divide. And so if I take the log, this becomes very simple. Right, so this is perhaps the reason why the sigmoid function is very useful. All these simplify. And if I plug that into this quantity, I get negative YZ, and then I have a negative sign there plus log 1 plus EZ. Okay. So you can see I absorb this sigma into the loss. I get a new loss, which I can call, I'm going to call this L log loss of Y and Z. Okay, it takes Y. And the second argument is no longer a probability, but when the interpretation of that characteristic. Anyone can. So you can see it here. Z is so sigma Z is on the interpreter of sigma Z is the probability, right? Probability of 1. So this is log of probability of 1 divided by probability of 0.
Or
This is odd ratio and this is log odds. Okay. So Z has a log odds meaning, and it can be negative infinity to infinity. Okay. So instead of measuring the loss from Y to probability, it can measure it to its log odds, or sometimes called logic in the general literature. So logit or log odds. And in fact, if you go back up, you can see that this logistic regression, in logistic regression, log odds basically is what we found is this is going to be just theta transpose xi. So this modeling is equivalent to saying that the log of the ratios of these equality theta transpose. We model the log odds as linear x rather than. So log odds can be anything negative infinity to infinity. So that's the equivalent formulation in any case. So we're modeling the logits. So this is the loss between y and the logits. So in terms of these, I can write. So theta hat would be argument 1 over n summation I from 1 to n. This loss yi, and then zi here will be theta transpose xi. We no longer have the sigma. Now this is very close to the linear regression because when I replace this log loss with the quadratic loss, I just get the linear regression. With this log loss, I just get binary classification. Although, yeah, so if you just create a quadratic class, this is binary, it doesn't make much sense, but you can actually do it. You can replace it and do classification with quadratic loss. And it's not necessarily that bad. But this loss is connected, this log loss is connected to everything in the logistic regression. So logistic regression. And note in the ERM form, the above is also an ERM version. I will note the similarity to linear regression. Okay. In particular, if I don't like linearity, I can replace this with a linear function of a more complex function. So maybe something beyond that is regression. Okay. There's a different log loss, which is it's a homework problem. So you can see if you instead of representing y, I have 0 and 1, but you're replacing with negative 1 and 1. Sometimes in binary classification, people do negative 1 and 1. Then you get a different form, which is even simpler. And that's also in the exercise that I'm going to assign. That would just take just the logits. There's no longer yi, just work them. It's like log loss applies to that. But we call it different things, but we see this both in the literature and it's sometimes confused. But just be aware that depending on how you encode yi, you get different forms of encode. And some people might not even call it log logs. This version, maybe the other one will be called log logs. Okay, sounds good. So once we arrive here, we can now do the estimation. Questions? How do we do the estimation? We just solve this optimization problem. It's convex. It doesn't have a closed form solution, but it's convex. So you have to look at it as function of this. So it's linear combined with this. So you can argue that as long as this loss is convex, then this is going to be convex because the composition of linear function. So is that log loss convex? Is it? Why? So I have to differentiate. First derivative is negative y plus. Right, and then the second derivative. So you can actually ignore this part because the first term is linear, so you can ignore it. The second term matters, but you can see it goes away. The second derivative. You can also write it as 1 plus e to the negative z. Right, and the second derivative would be 1 plus e to the negative z squared, right? There are two double like negatives. There's negative of this comes out, and then there's a negative because it's 1 over that. So this is, in the end, this is positive, strictly positive. So it's actually strictly convex over the entire real line. So because it's convex, we hopefully have like little trouble optimizing. So if you gradient descent, I'm hoping that I'm going to descend code to the global minimum. It's just that this has potentially a very flat part because you can see as z becomes close to negative infinity, so as z goes to infinity, e to the z dominates, and you get the second term would be very similar to a linear term. But as you approach negative infinity, oh, actually, okay, there is also going to be linear. But it's tricky, so we'll see. I mean, this is not like quadratic loss. So sometimes it takes a long time to converge to the minimum. And there are cases in which the minimum occurs at infinity. So you might not even converge, so you go to infinity. Because a lot of flattens out all the way to infinity. Yeah, but that's maybe later. But this is convex. I can, even if it wasn't convex, I could do gradient descent. It's a smooth loss, differentiable, and so it has a gradient. I can compute the gradient. If you learn about PyTorch, you don't even have to worry about calculating the gradient. You can calculate so the derivative of the loss is easy, and this is linear. There's a composition on the loss that we know the derivatives, and then so PyTorch knows about it. So you can think of it. I'm going to do some examples shortly. But any questions about this? Yeah.
Explain again, why you want to take the second derivative of that?
I wanted to show that this is convex, and function like differentiable functions convex if and only the second derivative of positive. Yeah, convexity is so something that looks like this is convex. So if I take 2 points, the function lies below this line segment, 2 points. And if things are differentiable, so this is equivalent to for differentiable functions for the tangent to tangent line to be increasing. Like, so if you look at the tangent line, the slope increasing. The slope increasing when the second derivative is positive. Okay. A function which is not convex is something like that. I'll take 2 points, I connect them. The graph is not entirely below. And these things you can see can have multiple local minimum. So if I do gradient descent, for example, so if my function is like that, so I might have something like this. Right, this is non-convex. If I start gradient descent, let's say at the point here, I start here, the derivative points to this point, and I'm going to here achieve like a zero gradient here. So I'm going to converge to this, which is local minimum. I'm going to converge to that. Okay. So you're going to start at local minima. Things are even worse in higher dimensions because there are points at which the gradient is zero, but it's neither a minimum or a maximum, because you could like, it could be a saddle point. So you decrease in one direction, increase in another direction, but almost flat, like the minimum. So you might converge to that. So if the loss is not convex, I have to worry about that. Although people in machine learning don't worry too much about that. But here you don't have to even worry about it. I showed that the loss is convex. So once you write down everything, so this is going to be a function of theta in high dimensions, but it's like ball shape. It might not be exactly like quadratic, so most likely it would like be something like this, or usually it goes to infinity, or like maybe like the slope would be different, but I'm going to show you the contours. In high dimensions, convex functions are a little bit more complicated, but not too complicated because of this property. You can have different like values, and stuff like that. Okay. So before doing that, so we have now recipe. So this can be applied to any training data. I don't have to have actually, the model doesn't have to be true. So in practice, you don't know the model is true, but you have to know that this came out under some assumptions, under like very specific assumption on the regression function, which may or may not be true. And that's the log odds is linear, or the regression function is sigmoid of the linear function. I just want to, in practice, you can like generate data from the same model and then evaluate it, or run it on real data. So there are these different approaches. So I just want to a generative model. So I can couple this like the logistic regression with some distribution of X, then I have a full generative model and I can generate from the logistic regression. So for example, if I let's see, I should be there. Yeah, for example, suppose I generate X for a normal with mean 0 and some covariance matrix. Say we're in 2 dimensions. Let's say X is in RD. So X is RD. Y is 0, 1. So I can generate the standard normal random vector and then say, okay, P of Y equal 1, given X is equal to X is sigma theta transpose X. So that defines a full joint distribution on X and Y. Okay, then I can generate training data from this. And let's say there is a true theta star, similar to regression, this could be like theta star transpose X. So this theta star is what I like plant in the model. And then I can do the NLE and ask if my theta that I estimate is going to approach theta star. Do I get consistency? And that's the hope that eventually, once you get more and more samples, this would happen. But this is like the best case scenario. So this is generating data from the model that actually follows my assumption. It's very similar to if you have regression, linear regression, just generate from the linear regression model, then try to fit it. And so I don't have to worry about the bias, basically, that my model cannot capture this relation. So this relation there is some parameter, like true parameter actually would satisfy. So I could get the true parameter, although for finance, and I'm not gonna get it. Okay, so that's this. I just want to give you a picture of what this would look like, to have an idea of the level sets of this. So what would happen is, I'm gonna generate x's, right? X is gonna be like Gaussian more here, less outside. So it's like circular. So you know like what a two-dimensional Gaussian like this would look like that. Then what happens is that this theta star defines a direction, right? And so the probability, so the level sets of this would determine the locations in which I have more probability of, or less probability, or the same probability of y being one. So for example, if I set sigma theta star transpose x equal to 1/2, all the x's for which this equation holds have equal probability of being 0 or 1. Okay, so these are very difficult cases. Versus if I have like sigma of theta star transpose x is like 0.9, these are very much in class 1. So occasionally with flip. So when all the x's for which this happens have a high chance of being class 1. So what happens if I do something like that? So what is the location? So if I look at the set of all x's such that sigma theta star transpose x is equal to 1/2, how does it look like? So this is in fact the decision boundary. You imagine this is the probability. This is the regression function. So the optimal rule here, so there's an optimal rule. Call this f star of x. If I knew the theta star, the optimal thing would be to detect this. If bigger than 1/2, 0 if sigma theta star transpose x is less than 1/2, and at 1/2 it would be the decision boundaries. It doesn't matter what I do, but it's like the hard thing. So this is really defines the decision boundary. Okay. So what is this set? So okay, so sigma is 1 plus e to the negative, as they call it, z. Sigma z is that, or e to the z, 1 plus e to the z. And then their sigma inverse, we actually implicitly figured out, is going to be, I'm going to apply it to p because it has the interpretation. So sigma maps logits to probabilities, and sigma inverse pull them back from probability to logits. So this is going to be log p1 minus p. So this is the inverse of that function. So basically sigma inverse sigma z is going to be z. So this you can easily convince yourself. So the sigmoid has the logit, the log odd as the inverse. So the easy thing to do here is this set is going to be exactly equal to, I apply sigma inverse to both sides. Okay, if I apply sigma inverse, I get theta star transpose x is equal to sigma inverse 1/2. So what is sigma inverse 1/2? 0. So this is going to be just x. Theta star transpose x is equal to 0. So this is the decision boundary. So what does it look like? Theta star transpose x is equal to 0. It's a hyperplane. Yeah, plane, hyperplane. So in R2, what it would be? Like the plane, like the entire space is a plane, right? Is it the entire space? Or?
No, like a line.
A line, yeah. So it's a hyperplane, two-dimensional hyperplane, which is just a line. Okay, the fancy hyperplane would be like really a plane, but in R2 it's just going to be. So it's going to be a line. It passes through, let's say, could be something. It doesn't have to be like 45 degrees. It passes through the origin, as you can see, because x equals 0. Okay, so what is the direction? Or what does the direction has to do with theta star? Theta star is going to be orthogonal to it, okay? So let's say this is, if that's the decision boundary, that could be theta star or the opposite direction. So you specify theta star, this defines the decision boundary. Okay. So the direction theta star determines which side is 1, which side is 0. Okay, so you can easily see that if I do something like that, then so this is equivalent to theta star transpose x being sigma inverse of 0.9. Right, sigma inverse of 0.9 is, so this is going to do, is this bigger or smaller? So theta monotone, so if this is higher, it's going to be higher than 1. So this set is going to be somewhere here. Okay. So this is this corresponds to shall we call it like eta? Okay, eta star. This is eta star x is equal to 1/2. This is eta star x is equal to 0.9 and so on. Okay, and then if we go in the other direction, this for example could be eta star x is equal to 0.1. Okay. So when you generate the data, the things that are here on this or above have like 90% chance of getting label 1. The things that are here have a like 0.1 chance of getting label 1. It's mostly 0. As you get closer, things here are more random. Okay, so you get mostly like label switch. So that's how it is. So when you generate the data, you can see that these like there's this grading of labels. And then so what the eta star does, or what the optimal rule does, is that it's going to assign 1 to everything above the dotted line and 0 to everything below. And it's not going to be in practice true because some of these, like at this point, they have like a chance of 0.5 of getting a label 1. Here it's not like 100% once you move it. Still there is a chance to get label 0. So the optimal rule is going to do like assign 1 here, and the fraction of errors that you get, the fraction of 0 above this can be the basically Bayes error, the limit of the problem. Because you can't do better than that. Okay, and that determines the level of the noise that is in this problem. Okay, so there is a fundamental limit in this problem, which is basically the fraction of the points that are 0 above this line, because the optimal rule is going to assign 1 to everyone. So like geometrically you can see what that would be. And then you can figure out how you can control this level of the noise. Anyone knows how can I like dial it down and up? Like I have a parameter in my hand, theta star. So what would happen if I want to increase the noise in this problem, like the fundamental level? So
Probably reduces the line.
this low.
And the primary.
I want to keep this low. I want to keep the decision boundary, but I want to like tune the level of the noise around the boundary. Too noisy or too sharp, that's what I want. Is there something that I can do with data stuff that keeps the decision boundary the same, but tune the level of the noise?
Magnitude of it.
Sorry?
The direction might be same, but the magnitude.
The magnitude, yeah. So the direction, keep the direction the same, but by varying the magnitudes. So you can see the direction. So the magnitude doesn't change the decision boundary here, because if I multiply theta star by something, but the direction is the same, that like multiply by something is going to cancel the loop. So this direction is going to remain the same as long as the direction of theta is the same. But if I increase the magnitude of theta, this point is going to happen faster. So like if I move a little bit away from the boundary, like suddenly at 90% of the time, So you can see it's like because of the nature of the sigmoid, goes from, so at this point at 0 it's 1/2 and then goes to 1. So if I have a very large magnitude theta star, if I move a little bit away from the boundary, theta star times x would be very large. So end up like landing quickly here. So I can basically control. So another way of saying it is I get the p of y equal 1 given x is equal to x. The sigma of the norm of theta star and then theta star divided by the norm of theta star transpose times x. Okay, so I divide and multiply by the norm of theta star. So the norm of theta star is just the L2 norm, the magnitude. Theta star divided by the norm is the unique norm vector, this point in the direction. And this like controls the difficulty. So if I call this U star, for example, and then let's say define a sigma tilde of, let's say, z to be sigma of theta star z, then this is like sigma tilde of U star transpose x. Okay, and this function I can plot, and this function is not gonna, the slope is gonna change. So if the norm of theta star is very large, it's gonna sharply switch from 0 to 1. If it's like the norm is very small, it's gonna like do this. Okay, so you can see this is sigma t. So norm of theta star small, norm of theta star large. So effectively, I'm having this parameter that can tune the slope of the thing, and so this defines the direction. And this new thing, sort of, you can see like when it's sharp, moving a little bit away from the boundary is just quickly point you towards so this sigma tilde z. Get if you want. Like I said, I can tune the level of the noise in the problem by choosing the size of data set. That's what I wanted to mention. Because some people would generate from like do this and then flip the labels randomly. Like by flipping the labels, they want to let's say if you want like generate from a logistic regression problem with some level of noise, people what they do is do this and then flip the labels widely, like some probability. Okay, so that would tell someone else that you really didn't understand much about the segment. This already has a built-in noise, and you can just vary it by changing the size of theta star. So there is noise built into the model. It's not additive noise, but it's like controlled by how large the theta star is. The direction is not defines the boundary, like the shape of the boundary or the direction of the boundary, but the size determines how noisy the problem is. Okay, sounds good. So for that reason, it's a little bit tricky. So estimating theta star, it's not like in regression where you have a theta star parameter and then you have like additive noise. So you have two different parameters that control the one controls the regression function, and the like sigma squared of the noise controls the noise. This single parameter controls both like the shape of the function and also the noise level. So that makes it tricky. Okay, any questions? So this is like the general picture of what the logistic regression looks like. You can see that decision boundaries are sort of linear. And that's where the linear, everything sort of essentially is the equivalent of linear relation. So you have decision boundaries that are linear. So if you have a problem in which the decision boundary looks like, so you plot your data points, and you see one class is, for example, here, the other class or envelopes this like that, right? This is like, it suggests that the decision boundaries may be something like that. This is not a good candidate for vanilla logistic regression, okay? Because the lattice regression, we're gonna try to like find the best linear separation. And this is not like, so you have to do something else there. But let's say the breast cancer data that we looked at, it looked like there is a linear separation that's gonna work. If you have linear separation, then this lattice segregation is nice. Questions? Okay, so next time we come back and do some like simulations, codes, and show you how you can do this property in Python. PyTorch basically you just have to modify our loss function, just change one line. And you're doing lattice regression. It's the linear regression. Sounds great. Thank you guys. See you next time.